In this lecture, we're going to pull together a bunch of the concepts that we've been dealing with in regards to engineering economics. And we're going to look at a kind of a fictional example. It's actually the one I introduced at the beginning of these talks about engineering economics, which was that construction of a bridge to replace a ferry service. So we're going to look at that and calculate the net present value to see if it's worth going ahead with the project. All right, so what do we mean by net present value? It's really taking the sum of the present value of all the costs, the benefits, and the revenue. Some of these benefits can be intangible, but we have to put a dollar number on them. And in fact, we did that. If you recall, we looked at the wait time that people might have experienced using a ferry and attribute some dollar value to that. So if our benefits are positive and our costs are negative, if we add them all together and get a positive value, as we say here, that essentially means that the benefits are greater than costs, and so we might green light that project. In other words, we might go ahead with the project. It can also, this net present value can also be used to compare multiple projects in which you might select the one with the highest net present value. And we're going to look at comparing multiple alternatives in not this week, but another week. All right, so here's the project we were talking about, replacing a ferry service with a bridge. And we have this kind of fictional case of 1 million persons per year traveling over this bridge, traveling over a ferry, and 10,000 trucks per year. Not a huge traffic for a bridge, but pretty substantial for a ferry. I guess you'd have a very large ferry traveling, say, every half hour. It could, I guess it's possible. All right, so that's the project we're looking at. So the benefits are as such, and these numbers have changed a little since the first lecture. Don't get alarmed by that, but I've changed them just to get them to kind of work out the way I wanted and to get for various reasons. So the value to individuals and save time, presuming their time's worth $9.50 per hour. We have 1 million persons. We multiply that out. We end up with $4.75 million in savings. That would be per year because we have 1 million persons per year traveling over the bridge. Value to business, we have trucks traveling over the bridge, and each one is has a value of $50 per hour for each truck. And there's a half-hour travel time over the bridge, over the ferry on average. Then we're looking at something in the neighborhood of 0.25 million. Now you can actually just add these together and we end up with a net of $5 million benefit per year for the life of the project. And we're looking at a 30-year project life. All right, design construction, $50 million, not a big bridge. A big bridge would cost substantially more. And the maintenance, initially it's going to be 200,000 or 0.2 million per year, and it's going to grow at a constant rate of 0.2 million per year. So initially it'll be zero. Then after 30 years it will be whatever 30 times 0.26 million dollars. Or yes, I believe so. All right, so those are benefits, those are costs. Now it looks like what we could do, first thing you do is to put this into a cash flow diagram. And so you see our costs, we have a 50 million initial cost, and then we have essentially an annuity or an annual expense of 0.2 added to that a gradient of 0.2. That's on the maintenance side. And then we have a constant benefit of $5 million. So all these are in the millions of dollars. This is actually incorrect. This should say millions of dollars. All right. So what we're going to do is I'm going to create this table. It's going to have the expense or the benefit. And you recall there are essentially three. There's the design construction, save time, and then the maintenance. And then we're going to have the type of expense, how much it costs, And then the factor. These are the factors like the P over A, P over G factors that we might deal with. So to start with the design construction, it's basically a single expense in year 0. So it's already in year 0. So the present value is actually the value, the initial value, which is 50 million. Notice I put a negative on it because it's an outgoing expense. All right, the next one is save time. You recall that's basically a uniform expense, uniform annual expense of a uniform annual benefit of $5 million per year over a 30-year period. That's our 30-year project or planning period. Now the maintenance, you might recall, started at 0.2 and then it increases by 0.2 each year. Or so we have a annual uniform expense of 0.2 million and then a maintenance gradient of 0.2. So it's increasing each year. It becomes a higher maintenance. As a bridge gets older, you'd expect it to have higher maintenance. They all have 30-year, essentially that's a project life that we're going to use in calculating our factors. Okay. Now I've given the formulas for calculating this. All right, so now we've actually calculated these factors using a interest rate or a discount rate of 4%. R equals 4%. And so here are the values: P over A, 17.292. Again, P over A, so that'd be the present divided by the annual expense for a uniform series, 17.292. And then P over G, that'd be present over the gradient, 201.06. So this uniform gradient, even though these values are the same, the uniform gradient, it's increasing, basically starting at 0 and increasing by 0.2 each time. So it has, over the 30-year period, ends up with the values as high as 5.8. So that's why this value, 201, is much greater than the annual P over A value, for which that annual value does not change. Okay, so then we can multiply these factors times our expenses here. So -1 times 50, negative 50 times 1 is negative 50. 5 times 17.292, 86, is obviously rounding off here. Negative 0.2 times 17 is negative 3, and negative 0.2 times 201 is negative 40. You add these up, 50, 93, 86, you end up with negative 7. Essentially, you're ending up with a net present value that's negative. It means that our present value of the costs exceeds the present value of the benefits. So someone might say, that means no go for the project. But in fact, these are pretty much political decisions. So it wasn't that far off from having basically 0 benefit. But you may also look at other benefits. There may be health and safety might be a benefit, social benefits for elderly might be served by a bridge, tourism, other business. So you might go back and try and quantify some of these other benefits, and you might find that in fact you end up with a positive cash flow. You might also want to look at an alternative bridge design. Maybe there's a smaller bridge that might come up with lower design construction costs, come up with a positive value. And ultimately, as I said, this is a political decision. Frequently, these are political decisions, and it's likely that you may find that people might just decide to proceed anyways because they decide this is something that's important for the future of this community. All right, so we're done for now with the engineering economics lectures. We're going to go back next week and look at another method of, we're going to look at the comparison of multiple alternatives.